Today's video is about the shape of molecules. So in our last video, we learned how to draw the Lewis electron dot diagram for a molecule. And now once you've drawn that Lewis electron dot diagram, you can use that information to determine the shape, or what we refer to as the molecular geometry of the molecule. And this idea of the shape of the molecule is based on what's called the valence shell electron pair repulsion theory, often referred to as just VSEPR. Sometimes they will say it quickly and call it VSEPR, even though the S is before the E. I realize that. But that is the theory behind this idea of shapes of molecules, okay? And the shape of the molecule is based solely on the number of bonds and the number of lone pairs on the atom in question. So there can be lots of different shapes within one large molecule, and that shape is based on, again, how many bonds that atom makes and the number of lone pairs or non-bonding pairs on that atom. Okay, this part right here, a non-bonding pair will repair more strongly than a bonding pair. We'll talk about what that means here in just a minute. Okay. In terms of predicting the shape, multiple bonds, so a double or a triple bond is just considered one bond. Whether it has a double or a triple bond, that still just counts as one bond when you're talking about the shape of the molecule. Okay, so how do you do it? You draw the Lewis electron dot diagram first. You count the number of electron pairs. So you count the number of bonds and then the non-bonding pairs on the atom in question. And then you use this table here for right now to learn them, but in the long run, you just have to know them, okay? So basically, to me, the important parts here are these numbers right here. How many pairs, how many bonds, and how many non-bonding pairs there are. And then the three bond angles you should be familiar with are the 180, the 120, and 109.5. So if it has a tetrahedral shape, it will have a 109.5 degree bond angle. And then really the big one here is, this is the actual shape right here, is this column. I'm not crossing that out. Sorry, that was a bad thing to do there. Okay, all of these here, these are the shapes that you need to be familiar with. Okay, and we'll talk about how to use that here in just a second. Okay, and then they have examples over here on the right-hand side, but really it's the number of bonds, the number of lone pairs, and then the geometry or the shape of that molecule. Okay, so using the VSEPR theory, predict the OCN bond angle indicated by the arrow in the diagram of compound W. So we see the arrow pointing at this carbon. Okay, and so the way that we determine the shape of that, the shape around that carbon right there, is we look at the carbon here and we count the number of bonds that are made to that carbon. So there are 3 bonds. Remember, a double bond counts as one bond. Okay, so we've got 1, 2, 3 bonds. And are there any lone pairs on that carbon? Again, don't look at any other element, just the carbon in question. No, it has 0 lone pairs or 0 non-bonding electron pairs. And now we can use the table for now, but eventually we need to know that if an atom has 3 bonds and 0 lone pairs around it, the shape around that carbon is going to be called trigonal planar. Not 2 R's. Trigonal planar. And I know that because when I come back up here, I see 3 bonds. So 3 bonds. See, it says bonding here. 3 bonding, 0 lone pairs. Come over here. That is a trigonal planar shape. Okay, and what are the bond angles? And again, they didn't ask for them, but if they did, that means that the angle, so you might even call it, for example, this angle right here would be the carbon-carbon oxygen. They could say that. What's the carbon-carbon oxygen bond angle in around that carbon? And you would say that is 120 degrees. Okay. All right, let's keep going then. Example 2. Using the previous structure, identify the molecular geometry around each of the nitrogen atoms in the compound. So there's 2 different nitrogen compounds. So let's go ahead And let's start with this one right here. So that nitrogen right there, again, has 2 bonds and 1 lone pair on it. And again, how do I know the shape of that? I'm either going to remember it. Some of the ways that help me remember is a lot of times I'll add those up and I'll go, okay, it has 3 electron domains is what you call it. Okay, and if all of those were bonds, it'd be like this one up here, it'd be a trigonal planar shape. However, you take a trigonal planar shape and take 1 bond away, what are you left with? So basically like X, Y, Y, Y. So that's a trigonal planar shape there. Take 1 of those away and put a lone pair on there. Okay, now you have, that's the shape right there. It's the same shape as a trigonal planar shape, but now 1 of the bonds is removed. Okay, and that is referred to as a bent molecule. Okay, now earlier it had said something about, before all of this, it had said something about bond angles. Okay, right here it said a non-bonding pair will repel more strongly than a bonding pair. So if you have to compare bond angles, what that does is it makes the bond angle a little bit closer together. And what I mean by that is, this bond angle here should be 120 degrees. Why? Well, because really it's a trigonal planar shape with 1 of those bonds removed. But, as that statement up above said, this lone pair here basically has more, because those electrons aren't tied to a bond, they're more free to move around, they increase the electron repulsion, which means they push on those electrons and those electrons a little bit more. So we don't need to know exactly how small that bond angle or the size of that bond angle, but we should know that it's a little bit less than, and I write that out just because the greater than less than sign sometimes can be confusing, okay? It's a little bit less than 120 degrees. They wouldn't expect you to know the exact number. Again, the only exact numbers they expect you to know are 180, 120, and 109.5. Okay? So in this case, you would know that if it's a trigonal planar with all 3 of them bonds, like right here, the bond angle's here, absolutely 120 degrees. Okay? The bond angle here in this one would be slightly less than 120 degrees. Okay? Now, the other nitrogen is over here. Okay? So again, we count the bonds, we count the lone pairs. 3 bonds on that nitrogen. So 1, 2, 3 bonds. 1 lone pair. Again, memorize it, or think of it as add those 2 together. That's 4 electron domains all total. So that's a tetrahedral shape. Okay, so take a tetrahedral shape, take 1 away, and what do you have left? You have an N that basically looks like this. You've got C and then the H's and the H's. Okay? Okay, and what's the shape of that? That is called trigonal pyramidal. Okay, and so the shape around this nitrogen right here is trigonal pyramidal. Again, they don't ask about bond angles, but if they did, what would you say? What's the bond angle here, or what's the bond angle here? In a tetrahedral, they're 109.5, but with that lone pair, it's going to be a little bit less than 109.5. Okay, so I would just write it as less than 109.5. And you might even say slightly less than 109.5. Okay, now let's compare that real quickly with, let's say, water. Okay, water looks like this. Okay, and one thing you have to be really, really careful with, it's in the note, I made it as a note up here, right here, is you cannot determine the shape of a molecule based on the way that you draw it. And by that, I mean, let's draw water. Okay, water, oh, water looks like this. Oh, it's making a nice straight line. That must be, here it is right here, it must be linear shaped. Just because you drew it that way, that's, of course, you would get, if they say draw the Lewis electron dot diagram of water on the AP test, that is 100% correct. Okay, that they would absolutely give you credit for that. Okay, if they say what's the shape of the water molecule though, and you say linear, you're going to get 0% for that. Because just because you drew it like this doesn't mean that's the shape. The shape is always based on the number of bonds, 2, and the number of non-bonding pairs, also 2. So 2 bonds, 2 lone pairs is not a linear molecule. It is, here it is, 2 and 2, a bent molecule. Okay, so therefore water absolutely is bent. Okay, now let's compare that to this the nitrogen one here. Okay, so I'm going to draw water again. I'm going to draw it actually as a bent molecule. Okay, and they say, tell me about the bond angles between those two. Is the bond angle in H2O, this bond angle here, greater than, less than, or equal to the bond angle here? Okay, and you go, well, they both have 4 electron domains, they must be the same. Wrong. Okay, if all 4 of them were bonds and not lone pairs, then absolutely yes, they'd both be 109.5. But this one, because of that one lone pair, is a little bit less than 109.5. And this one, with its 2 lone pairs, what does that do? It pushes on those bonds that still remain even more. And so this one would be even smaller than this one would be. So, for example, CH4 would be at 109.5. That's the tetrahedral shape. NH3, which again, you don't have to remember the exact number, but it's around 107 degrees. Whereas water, here it is around 105 degrees. Okay, notice how the bonds get a little bit smaller and smaller as you take bonds away and put lone pairs in there. Okay, let's keep going here then. So example 3, 2 possible Lewis electron dot diagrams for HN3 are shown below. So diagram 1, diagram 2, looks like we've got a triple bond in this one, we've got a double bond in this one. Gosh, then they give us a whole bunch of information here, blah, blah, blah. Okay, part A says, use VSEPR theory to explain why diagram 1 is consistent with the experimentally determined bond angles around NX shown above. So NX is this one right here. Okay, now why is diagram 1 consistent with that, where diagram 2 is not? Well, again, let's think about what we just talked about with bond angles. In diagram 1, we've got 1, 2 bonds and 1, 2 lone pairs. So that's two bonds and 2 lone pairs. That's 4 all total. And 4 is a tetrahedral. And a tetrahedral has a bond angle around 109.5. Okay. Oh, and what do you know? What's our bond angle here? Our bond angle is right around 109. Okay. If it were diagram 2, you've got 2 bonds and the 1 lone pair. So that's 3 all total. And if that's correct, 3 makes a trigonal planar shape. Trigonal planar shapes have bond angles of 120 degrees. So that bond angle right here would be 120, where here it's, again, around 109.5. Okay? So why is it consistent? I would say because there's 2 bonds, 2 lone pairs, which are going to produce bond angles of around, you could even mention the word tetrahedral. Okay, a tetrahedral shape that have bond angles of 109.5. And then if you want to mention diagram 2 would be around 120 degrees with its 2 bonds and 1 lone pair. Okay, and then part B says, explain why diagram 2, okay, so let's get rid of this here. Explain why diagram 2 is not consistent with the experimentally determined bond lengths. So they're saying here the bond length is 124, here the bond length is 113. Okay, notice that here you have, in diagram 2, you have a double bond right here. Okay, double bond, triple bonds are the shortest, single bonds are the longest. So in this case, you've got a double bond here and a single bond here. And therefore, you would predict that double bond has to be shorter than the single bond does, because double bonds are shorter than single bonds. Okay, but then you look at the actual numbers, and what do you see? You see that bond angle, that bond length there is 124. It's longer than the other one. Okay, so you would just say something about how, and again, I'm not writing out the exact answer for you because I want you to write it out, but I'm going to say something about double bonds being shorter than single bonds. Okay, and that would be all you would need to say on that one. Okay, our last one says an unknown gas D reacts with fluorine gas to form the compound DF4. A student claims that if element D is in group 18, oh gosh, first of all, let's figure out where group 18 actually is. Basically, you start on the left-hand side, you just start counting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 is the noble gases, okay? So if you have a noble, and again, you can just choose anyone you want. It would be, let's choose argon, because really they all have the same number of valence electrons, except for, of course, helium, okay? So argon, so let's say it's ArF4. And again, whether it's Ne or Ar or Kr or Xe, it doesn't matter. Okay, what would the shape of that molecule be? Would it be a tetrahedral? Okay, so we have to draw that. We have to draw the Lewis electron dot diagram. So we'd go Ar, F, 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 F. We know we have to count the electrons. That's 36. So I'm just following my steps for drawing the Lewis electron dot diagram. So I've used 32. I have 4 left over. Where do leftover electrons go? On the central atom. Okay, so again, whether it's argon or krypton or neon or xenon, that shape is exactly the same for all of them. Is that a tetrahedral shape? Okay, of course not. No. Okay, I'm going to absolutely disagree with that statement. And you could go about it 2 ways. You could say because a tetrahedral has 4 bonds and no lone pairs, or you could say this has 4 bonds, and then you could say, and this has 4 bonds and 2 lone pairs. That would be perfectly fine, and then you could stop. Or you could try to get really fancy and say, well, this one has 4 bonds, 2 lone pairs of electrons, and what shape does that actually produce? If you happen to know it, it is a square planar shape, not a tetrahedral. Either of those 2 ways would be perfectly fine.